How's it going, ladies and gentlemen? It's Johnny here again, looking at 16.9 stuff. All right, kind of short. We want to be able to predict a salt's effect on pH based on the cation and anions that they produce. So let's take a look at some of these problems. If we had a zero point 0.1 molar solution of blank, uh, it would have a neutral pH, right? So which one of these would be true? The way you got to do this is you got to look. All right, well, Na2S is going to break up into Na and S. So let's look at their acids and bases, right? Na would be like NaOH, and S would be H2S. Well, let's think about this. That is a strong acid, and then a strong base, and then a weak acid. So what would happen in solution is the Na would break off, and it would be like OH minus whatever. I don't need to hang out with you. I'm a strong base. I'm not gonna, we're not gonna hook up and hang out. Whereas this H2S, the S ion, is going to be floating around just looking for homies to chill with. Be like, yo, hydrogen, where you at? I need to chill. We need to hook up. And then when we hook up, we're going to stay together. So that's going to change the pH, right? That would make it more basic because it's taking away the H+. So neutral, not A. KF, well, it would be like getting KOH and HF. So this is another example of a strong base and a weak acid. So if we put KF in solution, again, the K plus isn't going to hang out with the OH minus. It's going to completely dissociate. But the hydrogens in the fluoride ion, they're going to hang out together, and that's going to change the pH. All right, C would be like getting NaOH and HNO3. So in this example, well, we got a strong base and we got a strong acid. So it makes sense that if you mix those two things together, you get a neutral pH. Because what would happen is the Na plus isn't going to hang out with the OH minus because it's a strong base. Same with the H plus and the NO3 minus. They're not going to hang out because they're a strong acid. So that's not going to have an effect on the pH. Let's take a look at the other ones. Well, I'd get NH4 plus OH minus and HCl. But basically this is going to give off another H plus, isn't it? And then so is this HCl. So this isn't going to remain neutral. Same thing with Na and F. We're going to get basically NaOH, which is a strong base. They're not going to hang out at all. And we're going to get HF, which is a weak acid. So they're going to actually get stuck together and change the pH. So the only one that would stay neutral would be choice C. All right, same thing but different. An aqueous solution of blank will turn litmus blue. All right, so we're looking for something that's going to make it a basic pH. So if we take a look at the NH4ClO4, this is going to be acidic, right, because of that NH4. So it's definitely not going to be A. We get K and Br, so it's like KOH and HBr, which is a strong base and a strong acid. So that's going to stay pretty neutral still, so it can't be B. NaCl is going to break up. We're going to have a chance for NaOH and a chance for HCl, which they're both strong bases and strong acids, so it's going to remain neutral. NaHSO4, well, we're going to get NaOH, strong base, and possibility to get H2SO4, which is a strong acid, so that's going to stay neutral. But now if we take a look at Na2SO3, we're going to get a chance for NaOH, which is a strong base, and HSO3 minus, which that SO3 minus wants to take up two hydrogens because it's a weak acid. So if we have a weak acid, it's going to suck up more H pluses, which is going to turn the solution basic. All right, number 3, we got a tough one. They give us what is the pH of an aqueous solution of KF, and they give us the Ka of hydrofluoric acid. They give us a concentration of KF. All right. So first, well, let's talk about what's going to happen in solution. In solution, we're going to get the fluoride ion reacting with water to give us HF and OH minus. All right. So that's the basic thing, but they give us the Ka, right? So this is acting as a base, so we want the Kb. So we got to go, all right, well, I know that Kb equals the Kw, which is 10 to the minus 14 over Ka. So let me solve what my Kb is first right now. Beep, bop, boop. I get 1.43 times 10 to the negative 11. That's my KB. So now I'm going to have to use that KB expression, which would be, the HF times the OH minus all over the fluoride ion concentration to figure out how much of each thing we got. So I'm just going to, how much HF do I get? X amount. I'm going to get the same unknown amount of OH minus. It's all going to be on top of 0.35 molar minus the amount that we used. So that is my KB expression. So that's going to be, x squared over 0.35 minus x. I'm going to do just some algebra, rearrange that so I get it into that polynomial structure that I'm familiar with, and I get x squared plus that KB times x minus 0.35 KB. So now I can plug in my quadratic equation, solve for x, use the x that makes sense, and I get x equals 2.24 e to the minus 6, and that is the molarity of the OH minus. And that's just what I solved for. So now what I'm going to have to do is go, alright, well, if I want pH, there's a couple of different ways that I can do this. One is to take the pOH and then figure out the pH that way. The other way is go to, alright, well, if I know the OH minus, I can figure out the H plus concentration. I'm going to do it that way. So I go, well, I know H plus times OH minus has to equal that KW, which is 10 to the minus 14. So I know that H plus has to equal KW over the OH minus concentration. I know those two values, so I plug them in, and I get 4.47 times 10 to the minus 9. So now that's my H plus concentration, and now I just go, alright, well, pH equals negative log of that number, 4.47 times 10 to the minus 9, and I get the answer being 8.35 for my pH. That one was kind of a difficult one. Right? Sometimes it helps just to start doing stuff. Right? Alright, 4. The Ka of hydrocyanic acid at that temperature is this. What is the pH of an aqueous solution that has 0.08 molar sodium cyanide? So again, what's going to happen is the sodium cyanide is going to dissolve to give you the cyanide ion, which will react with water to give you the hydrocyanic acid, which I can't spell things because we can't, HCN, and the OH minus. So again, they give me the Ka, but the Kb is going to be what's useful to me. So Kb is equal to that Kw over Ka, both values I know. So I plug that in and I get 2.04 times 10 to the minus 5 as my Kb. So now I'm going to do like what I did in the other problem. We go, well, how much HCN am I going to make? X. I'm going to make the same amount of hydroxide, and the amount of CN minus that I got is going to be that 0.080 minus X, how much I used up. So I'm going to plug that in. I get X squared all over 0.080 minus X has to equal to KB. So now I just do some algebra, and I get X squared plus KB X minus 0.080 KB and equals 0. So now I can plug it into my quadratic equation. I solve for X. I use the one that makes sense. X equals 0.00126, and that is going to be for the molarity of the hydroxide ion. So again, they want the pH. I got the OH minus, so there's two ways you can do this. You can do 14 minus the POH, or you can go, well, what's my H plus, which is the way I'm going to do it arbitrarily. Both ways work. So I go, well, H plus has to equal that KW over OH minus because of that formula where KW equals H plus times OH minus which always equals that 10 to the minus 14. So now I got numbers, I plug it in, beep bop, boop. I get 7.89 times 10 to the minus 12 as my H plus concentration. So I just do negative log of that. And I get a pH of 11.1. Final answer. Tough problems, I know. Questions in class?